he kind of taught me stuff, and so yeah, I kind of learned from him. But yeah, I'm not good. I just don't have I don't have a lot of natural ability, but I do enjoy it. Yeah, I do enjoy it. Do you play, Chris? Ah, yeah, yeah. It's a good pastime, uh, and it's relaxing too. All right. Okay. So why don't we get started? It looks like we've got about 2/3 of the class here, or 3/4. Nah, close. Yeah, about 3/4. Um, so I am speaking right now. I will. I am speaking. I'll just send a message through chat for those of you who can't hear me. I know I tend to talk to those people who can't hear me, and I don't know why I do that. But um, if that does happen, people have told me that logging out and logging back in sometimes fixes it. So if that happens, just do that. Also, I appreciate it too if you let me know if my sound goes out. I did have some challenges with it during my lecture yesterday. But it was with a class that was about double the size, so maybe there was a bandwidth issue there. Um, so yeah, I'll appreciate that. So we'll start off today. No, it was 1:31. We'll start off today talking. I'll talk a little bit more about how things are going to proceed. So first things first. The exam next week's exam will take place, so it's going to happen at the regularly scheduled exam time. So midterm exam number 2 will be 1 week from today. So we will have the exam at the regularly scheduled exam time. We did get a notification from the dean that we're to try and keep things as close to the syllabus as possible. So some of the ideas I was spitballing last day, those won't happen. So we're going to have an online exam. I expect the midterm exam will be 1 hour. The final exam at the moment is scheduled as planned. So it'll be April 15th. It will, although they haven't, I guess, officially said there will be no final exam, in-person final exams, you can pretty much bank on it, I think. I can't see us returning. I can't see us returning before the exam period. Um, uh, if you do have a question, just put it into the chat. Okay, so Josh just asked, so no short time limit to prevent cheating. No, I will make the exam a shorter exam. So my plan is I'm going to do about a 1 hour exam. So that'll be the strategy with it. It'll be a 1 hour exam. So typically I put 75 minutes on the paper, and then I usually give you close to 80 minutes. Um, so it'll be 1 hour you'll have to finish the exam. The final exam, I expect it'll be 2 hours or perhaps 90 minutes. So time will be an issue. I won't make it as much an issue as I was talking last day. Um, yeah, I'm a little less concerned about cheating, and I really don't think chances are there will be some attempts on that, but I don't think for the few cases where that will happen, I don't want to disadvantage everybody to prevent the one or two students who might cheat. Uh, so no standard exam, just 15 minutes. No, I'm sorry, I must have misspoke. It will be um, it will be a full hour. That is what I'm expecting. It'll be 15 minutes shorter than my usual exams. So my usual midterm exams are 75 minutes. I expect next week the exam will be 1 hour in length. Okay, so you can expect to spend 1 hour in length. Did that answer the question there, Josh? No, I meant the exam will be just like others, just minus 15 minutes from usual. Yes, but it will be online. Yeah, so I'm still working with um, that tool. I made my first quiz yesterday, and yeah, so I've got a few more things to figure out for the quiz. I'll give you the day before the exam. I'll tell you a little bit about the exam if I can find the time. I might even put up like a little 5 minutes or 10 minute or 15 minutes practice quiz that will show you the way the quiz kind of works, so you can get a feel for how you submit something and the pages and that kind of thing. Um, all right, and I won't make it worth any marks. It'll be more just for you to try out. Okay. Um, all right. Anything else? Yes, the final exam. So let me just read something. I'm going to post something to Moodle. I sent it to Jim just to get his feedback on it. I didn't ask him to. He's very busy right now, so I don't need him to get back to me on this, but I plan to post this a little bit later on today. And if I do get some input, I may modify it slightly. But um, let's see. Yeah, the final exam will take place at the already scheduled time. So I think for this class, it was April 15th. The final exam schedule was created with student workloads in mind. So we've been instructed to keep these dates as much as possible. Um, Okay, and so that's kind of the key point here is, um, uh, that may be kind of the line that your instructors will be taking because I was thinking I might put the final exam on the last lecture period, um, but yeah, we've been instructed that no, that's a no go. Um, so we're going to try and stick with the usual whatever our regular plan was. That's what we're sticking with. All right. And lab assignments are still going to be done in the same way. So you had a lab assignment due this morning, and you're working on run one right now that will be due next week. Um, I will probably have common submission times for everybody rather than a Monday submission time and a Thursday submission time. And the reason for that is because now I'm just going to encourage everybody who wants to attend a lab to attend a lab, so we don't have a seating capacity that I have to be concerned with. So I'll run a Monday lab and a Thursday lab, and anybody can join in those labs. And then I think what we'll do is we'll make the assignments due on Thursday morning at 7 a.m. Okay, so lab eight, for those of you in the Monday lab, can assume that will be due. I'll be collecting those a week from today at 7 a.m. All right. I'm not sure how I'll get feedback to you. Oh, I'm not recording this. Thank you, Connor. I will do that right now. Thank you so much for that reminder. So I'm recording now. So we will where was it? Yes. So feel free to attend the Monday lab or the Thursday lab. So the way they're really going to work is they're really going to be more like office hours. I'll be here. I'll just be kind of hanging out. I'll probably be working on some other things, and then when you have a question, if you join the session, if you have a question, you can just interrupt me. I will probably, if it's a small group of you, what I'll probably do is, I'll give you moderator access, which means that you can post things to display, and we'll have a whiteboard that we can all write into. So, um, you know, we'll see how it goes. That's at the moment, that's kind of the best I can on Tuesday, and to the 131 students, and I was able to pop up Visual Studio, and so I could write some code and describe some things, and that kind of thing. Um, okay, any other thoughts or questions? So I will post that notification um, later on today to Moodle. Okay, so why don't we get started on getting back into some of the material. So I didn't finish deadlocks. So there was something in the topic of deadlocks I just wanted to talk about. It's really the last item there, the modified resource allocation graphs. All right, so let me pop that up. CPU. Oops. Keep forgetting to click the share button. Oh, wrong document. Okay. So we we worked with resource allocation graphs. So we saw an example of that. What we're going to do now is we're going to modify resource allocation graph slightly to so it can be something that we can use to determine if something is in a safe state, um, rather than just using the resource allocation graphs to determine if something is deadlocked. Okay, so the previous way that we used a resource allocation graph was to see if a set of processes are in deadlock. This algorithm is to see if a set of processes are in a safe state or an unsafe state. And so the idea there is we can use it to help us determine, us being the system, to determine if we should allocate a resource when a request comes in. Okay. So what we need is we need one other type of edge for our graph. We previously had two edges, a request edge and an assignment edge. So the request edge went from a process to a resource. Um, I'm just going to. Right, so that would be a request edge. And the um, when the resource is allocated to a process, the request turns to an assignment edge. Right, so it's an arrow that goes the other way. So those are the two types of edges. So now we're going to introduce an edge called a claim edge. And remember with um, uh, deadlock avoidance, the idea is you announce to the system what your resource needs are. And so that announcement is going to be, or we say you claim your resources before you need them. So we're going to represent that with an arrow, but this time it will be a dashed arrow. Okay, so that's a claim edge. A claim edge converts to a request edge when the process makes the request. So if I'm a process and I'm happily doing my thing, and I've announced to the system, I'm going to require resource number one at some point, there is a claim edge between me, the process, and the resource, right? Because at some point I could make that request. Okay, so it indicates that I could potentially ask for that resource. So there's always an edge between a resource and a process if that process could potentially request, if the process could potentially request the resource. All right, so a claim edge converts to a request edge when a process requests. When it actually makes the request, it turns into a request edge. So it basically just becomes a solid edge. When a resource is released by a process, so this guy here, when a resource is released by a process, meaning, I'm done with the resource, I can unlock, to mutex, I can unlock it, and the system can take it back. So that arrow that went from the resource to me, the process, that now kind of goes in the other direction as a claim edge, right? So when you give up the resource, it goes back to a claim edge because I have announced to the system that I could request that resource, so the system knows that I still could request the resource in the future. All right, so let's go to the next one. So now here's a situation. So on the left here, we've got two processes and two resources. So both processes will have announced or claimed to the system that they could at some point need both resources, right? So there are claim edges. If the processes are just getting started and they don't have the resources, there would be claim edges going from each process to both of the resources. Okay, so in the situation over here on the left, process one has been allocated resource one. So we've got an assignment edge going from resource one to process one, meaning process one, if it's a mutex, process one has waited on it and taken control of the mutex. So it got the lock. And over here, it shows process two has perhaps, say, requested the lock or requested the resource, but doesn't have the resource because it's currently occupied by P1. Okay, and so we've got claim edges. So the dashed lines are the claim edges. All right, and so now let's say process two, let's not overthink it, but let's say process two over here makes a request for resource two. Okay, so the question would be, so notice this is, what have I done here? Yeah, so let's say this turned into a solid line. So this goes to a solid line. Um, there we go. We make that line solid. So it's the request comes in. So the system now has to decide, well, this resource is available, that the process has made a request for it. It's available. Why not allocate it to the? Why not allocate the resource to the process, right? And so that would put us in this situation over here. We're not in deadlock, right? Um, process one could give up resource one, P2 could get it, and then it's all good, right? We're not in deadlock, but we can't prevent this process because it's currently running, right? And an instruction that it's going to make in the future might be um, to request this guy, resource two. And if it does make that request, then we would have a cycle and we would be in deadlock. So even though we're not in deadlock right now, and allocating this resource to P2 would not put us in deadlock, right? We should not allocate the resource to P2 because it puts us in an unsafe state, right? There would be no safe sequence, right? So, there's only two processes here. So the two possible safe sequences is P1, P2. And we can't, each has one resource and they both need two, and there are no resources available. So we don't have a safe sequence. All right. So, we could regard this. The obvious question is, wait a second, how can process two request a resource if it's stuck waiting for resource one? Yeah, and that's in this diagram that probably shouldn't have been presented this way. I think it does come from your textbook. It would have been better to have that as a request, as a claim edge, right? And so this thing should really be displayed as dashed if we're going to allocate this to P2. Okay, so in a resource allocation graph with claim edges, we use a cycle to indicate an unsafe state. Okay, if there's a cycle, we're in an unsafe state. Doesn't mean we're in deadlock. It will mean deadlock if the cycle is there are solid edges creating the cycle. Then it would mean it's in deadlock. But if we have a cycle and created with it, and there's dashed edges, then this identifies an unsafe state. Any questions on that? Okay, hearing none, I will move to the next slide, which I think, there we go. Great. Thanks, Josh. Okay, so just to summarize, the strategy again with allocation or deadlock avoidance is don't grant a request if granting that request puts the system in an unsafe state. Right? Let's see, cycle with dashed edges is unsafe state, and cycle with solid edges means deadlock. That's right. Yeah. So if we get to the situation where it's solid edges, it's a deadlock. All right. Okay, so we can let this go. So that ends the topic of deadlocks, and we'll move on to CPU scheduling. All right. Okay, so CPU scheduling, I think this is chapter 6 in your textbook. Textbook does a really good job with it. I pretty much follow everything that's in the textbook. Um, uh, so we'll go through that. It'll usually takes about a lecture and a half to kind of do this topic. Maybe a hair longer than that. Okay, so let's move to the next slide here. So so what's process scheduling? So let's remember what a process does. So a process goes through periods of um, uh, being on the CPU and executing its instructions, and then it will, you know, do an IO. We call that time that's on the CPU. We call that a CPU burst. So it's on the CPU for a little while, and then may finish, or may need to wait for something like some IO operation. And so we call that an IO burst. So if it makes read requests from a file, well, it's going to be removed from the CPU and go into the waiting state, um, and then wait for that IO request to be fulfilled. And then when it comes back from that, it'll go, the next time it gets the attention of the CPU, it does a CPU burst. And if it doesn't finish, something will, cause it to perhaps do an IO burst, and so on. So you can see that it alternates, processes alternate between CPU bursts and IO bursts. Okay, so what we care about in process scheduling is we care about a couple of things. Um, we want to determine the best strategy for scheduling, but it's really the CPU bursts that we care about. So the IO bursts, if we're scheduling the CPU, we really don't care about you know what's on the other queues, like um, a queue for a device or something like that. We don't care about that. We want to make decisions about which process should be on the CPU next, and we're only going to make that decision based on what processes could be put on the CPU next, and those will be the ones that are sitting in the ready queue. Okay, um, let's move to the next slide. Yeah, so let's before we kind of start talking about scheduling in more detail, it helps to kind of appreciate um, the nature of CPU bursts. Generally, they're pretty small. So most CPU bursts are small in duration. They don't last for minutes, kind of thing. They might be in the order of milliseconds, so a small amount of time before they might need some sort of input and output. And that's certainly going to be true with interactive programs as well. Really short little bursts, and then waiting for input. Right. So the burst frequency, um, uh, or the distribution of bursts, looks like that graph. So it's kind of spikes around um, a small burst duration, and then there are some bursts that are longer, but they're much less um, frequent. You don't see them very often. Okay, so let's go to the next one. And okay, so I'm going to try drawing something here. So just bear with me for a second. Oops. I practiced this before a lecture to see if I could do it relatively quickly, and yeah, it wasn't too bad. Taking the advice of some of you guys. Um, okay, so a process, um, when it first gets created, is a new process, and then um, it goes into after it gets created, it goes right into um, the ready state. So it basically means it goes into the ready queue. And then from there, it really only has one place it can go. Um, it can go into the running state. Running state, and so it would go from here to here, right? And from there, a number of things can happen, right? We saw that it can go into, it can finish, and that would be the terminated state. So it means it completely finishes doing its thing and it's all done. So that's CPU, and we're talking about a CPU burst here. So a CPU burst kind of arrives, no, the process is, yeah. After here, we're talking about a CPU burst. So it's in the ready queue, it gets running. If it finishes, it goes into the terminated state. And if not, a couple of things can happen. It can go into the waiting state. So if it makes a request for some IO operation, right, it'll go into the waiting state. And if not, it might, you know, be told by the system, no, you have to go back into the ready queue. Maybe you're taking too long, right? So it goes back into the ready queue. And then the other piece of this puzzle is when a process finishes waiting, you know, if it was waiting for some IO, it returns to the ready queue. It never goes back onto the CPU. Okay, so let's discuss each of the arrows in that diagram. Um, and when is the CPU making decisions about um, decisions about scheduling? Well, um, if something is, so when do decisions have to be made? Um, if a process finishes, um, so right there, if a process finishes, then nothing is on the CPU, right? So if nothing is on the CPU, should be pointing to it here. Nothing is on the CPU. Then the scheduler is going to kick in and say, well, I've got to schedule another process. So it's going to go to the ready queue and look for a process. So it has to make a decision at that point. All right. So I'll leave it in red when I'm making a CPU scheduling decision. Right. Okay. So I have to make a CPU scheduling decision. Oops. Sorry about that. I also have to make a scheduling decision if this happens, right? So the process makes an IO request. Okay, we've got a scheduling decision to make there. These two decisions, when they go to make these decisions, those decisions would be what we say is non-preemptive decisions, because the CPU is, nothing is on the CPU. The process took itself off of the CPU, right? So the system now has to decide what process should go on, right? So those would be non-preemptive decisions. Preempting means I'm taking the CPU away from you. Okay, so that's preempting means that. Non-preemptive means that the process finished. It voluntarily gave up the CPU. All right. So obviously, if you terminate, you're giving up the CPU. And if you make an IO request, that's just an automatic, you come off the CPU. So at those 2 points, scheduling decisions have to be made. Those are non-preemptive. The other times the scheduler could make a decision is whenever the ready queue changes, right? So if let's say a process returns from waiting, okay, now the ready queue now the ready queue has changed. So instead of there were 5 processes in the ready queue, now there is 6 processes. Now it might be the case that that process that just returned has, say, a really high priority, okay, and should really be given the attention of the CPU. So in that case, the if a decision is made at that point, we would call that a preemptive decision, or it's a yeah, I guess we'll be preempting the process that is on the CPU. Okay, so we would be preempting under those circumstances if we decide to take the process that's on the CPU to take it off of the CPU, right? So if we take the process off of the CPU, the system decides to do that. The process is happily running, um, and we decide to take it off as the system. We are preempting that process. Okay. Um, okay. So that guy there is preemptive. Um, yeah, maybe should give that a separate color, eh? Um, let's give it let's give it orange. There we go. Add orange in there. So we have to make a scheduling decision, but it will be preemptive. Um, Similarly, we might, if a new process happens to arrive in the ready queue, yeah, we could make another decision. It's now instead of 5 processes again, and now it's 6. So maybe that process should go on the CPU for some reason. Okay. The other type of preemption is, if we're running a system where we're a time sharing system where we're taking processes off the CPU at regular intervals. It's used up its turn on the CPU. We don't want it hogging the CPU. Then we take it off. All right. So this slide is kind of getting at that the scheduling decisions are made under certain circumstances, right? So when a process, so let me just point here. So when a process um, switches from the running state to the waiting state, the CPU's got to make a decision, right? That would be a non-preemptive scenario. Um, when the switches when the process switches from running to ready, that would be the preemptive scenario. That's this scenario here, right? When the process switches from waiting to ready, that is this situation, right? Um, if the scheduler makes a decision in these two cases, they're preemptive. But in the cases of 1 and 4, the process is voluntarily giving up the CPU, so those would be non-preemptive. The new process isn't considered here, but if we wanted to count that, that would be preemptive if a decision is made at that point. Okay. Any questions about preemptive and non-preemptive? All right. Hearing none, we will. I think I'm hearing none. Let's have a look here. Uh, oh, yeah, great. Yeah, thanks. Okay. Um, all right, let's move to the next one. Okay, so what's the next guy here? Okay, so this topic is looking at different scheduling algorithms, and obviously what we'd like to do is we'd like to kind of compare them. How does this algorithm compare to another algorithm? So we want to have some criteria. So there's a number of things that we could care about. Preemptive, just a question popped up. Preemptive is essentially a context switch from one process to another. Um, well, all of them are context switches. Preemptive means that we're removing, so we being, let's say, the scheduler or the system, removes the process that's on the CPU. We take it off of the CPU. That would be that's preemptive. Okay, so a decision where we kind of intervene and decide, oh, maybe a more important process has arrived in the ready queue. I'm going to take you off, so I'm preempting you. Okay, so that's the idea there. Preemptive means the system takes you off. Okay, um, so a non-preemptive would mean, once if you're following a non-preemptive algorithm, once a process has control of the CPU, it holds control of the CPU until it voluntarily gives it up. That would be a non-preemptive algorithm. So preemptive, non-preempt. Oh, yes, preemptive is just involuntary. Yes, yeah, yeah. That's a good way of putting it. Yeah. Um, okay. So the different scheduling criteria that we could look at. Let's talk about those. So CPU utilization. There's CPU utilization, throughput, CPU utilization, throughput, turnaround time, waiting time, and response time. So CPU utilization basically means let's keep the CPU as busy as possible. So that seems like, what we'd like to do is we'd like to, maximize that. Throughput means, um, is a measure of how many of the number of processes that complete their execution per time unit. So how many processes? When I say processes now, I'm now you should be thinking CPU bursts. Okay, so CPU bursts. How many CPU bursts get to complete per minute or per second or something like that? Right. That's throughput. Um, Turnaround time means the amount of time to execute a particular process. Okay, so that's the total amount of time that it takes from when the process arrives into the ready queue to when it is done. Okay, so when it finishes executing, how long did that take from arrival to being done? Okay. Um, then there is waiting time, which means how much time does the process spend in the ready queue? So that means, um, a process is, it arrives, it's sitting in the ready queue, and then it gets the attention of the CPU. How much time did it spend in the ready queue? It may go back to the ready queue, right? It may get kicked off of the CPU, and sent back to the ready queue. In that case, we would be adding both parts of that, the amount of time it waited to first get onto the CPU and the total amount of time that it spends on the ready queue, um, between every turn it gets on the CPU. Okay, so we should think the total amount of time that it spends in the ready queue for waiting time, and that's one that we're going to spend the most time with. Is that item? Response time is similar to waiting time, but it's the amount of time that it takes when a request is first submitted or first arrives on the ready queue to when it feels its first response. Right. So how long does it take for a process to kind of feel its first response from the CPU? So all of these things kind of matter, right? In an interactive system, response time is pretty important, right? If we run a program and we're trying to interact with it, but it's not responding, um, that as a user makes us feel uncomfortable. So we would certainly want to make sure that response time is minimized. And if we can't minimize it, we want to make it pretty predictable. If it always takes 1 second, that's fine because users will get to know, oh, it takes a second to respond. But if sometimes it takes half a second and other times it takes, 15 seconds, that would not be good because users will assume something's gone wrong. So just going to take something out here. So we would like to, so what do we want to do? Give me just a moment here. So we want to maximize CPU utilization. Right? We want to maximize throughput, right? Um, so we want to maximize those two things. And we want to minimize turnaround time. Waiting time. And response time. Does that make sense? So those are certainly criteria we care about, and we want to maximize some, minimize others, and but keep the response time consistent. Yeah, so we could get into some more complicated, criteria like making sure the standard deviation of the response time is fairly narrow. Yeah, so something like that. All of those things matter. But we'll just look at a couple of them. All right. Any questions on that? All right. So I'll just move on to the next one. Okay. So here's what we're going to do. So we're going to represent processes and their arrival in a certain way. So like a CPU burst, we're going to represent them like this. I'm going to say process one. I've got three processes, process one, process two, and process three. And let's say they all happen to arrive at roughly the same time, but they do happen to arrive in this order, P1, P2, P3. Okay, but they all basically arrive at, say, time zero. But just, P1 slightly ahead of P2 and P2 slightly ahead of P3. Okay, now P2 or P1 has a total, what its total CPU burst time is 24 time units. Okay, so it's going to be on the CPU for 24 units of time. P2 is going to be on the CPU for 3 units, P3 on for 3 units. So what we'd like to do is we'd like to evaluate, let's say the waiting time or the average waiting time for the processes. So what we're going to use is something called a Gantt chart. Um, and and that will help us kind of visualize the arrival of things and how much time things are spending on the ready queue. This thing too, we can kind of think of as the CPU, right? So, from time 0 to time 24, process 1 is on the CPU. It's on there for 24 time units because its burst time is 24. Meanwhile, while it's doing its thing on the CPU, P2 and P3, remember, arrived roughly at the same time at time 0. So they've been sitting on the ready queue all of this time, right? When P1 gets off of the CPU, CPU is now free, so P2 can go onto the CPU. So P2 would then be on the CPU between times 24 and time 27, and then it would finish, and P3 could get onto the CPU and would be on the CPU between times 27 and 30. So what we can look at is we can look at the total amount of time that each process waited. So process one, so now I'm talking about this second bullet here. process 1 waited 0 time units. As soon as it arrived, it got to go on the CPU because the CPU was available. At time 24, P2 got onto the CPU. So that meant it was sitting in the ready queue from time 0 to time 24. So it was waiting a total of 24 time units, right? P3 arrived roughly at time 0 also and didn't get onto the CPU until time 27. So its total wait time was 27 time units. So if we add up all three of those wait times, it adds up to 51. And if we divide 51 by 3, we get 17, right? So the average wait time in this case was 17 time units, all right? So that's the way that we're kind of looking at this. So let's move on to the next slide. So let me just go back for a second. So notice, right now we'll see that what happened here is, P2 and P3 had to wait a long time, right? Because P1 was a really long process. Its burst time was quite long. So if we just happen to, get lucky, and that instead of P1 arriving first, if P1 was, say, just slightly behind the other two, and P2 arrived first, and then followed by P3, and then followed by P1, what would be the wait times? Well, the Gantt chart would look like this, right? P2 would be serviced right away. P3 would be serviced after time unit 3, and then P1 would be serviced starting at time unit 6, right? So the wait time for P1 would be 6, the wait time for P2 would be 0, and the wait time for P3 would be 3. So if we add up the wait times in this case, it's now 9 divided by 3, which is 3, which is a pretty drastic improvement from 17, right? So why did we get a much better performance? Well, it was because we kind of had this convoy effect, right? In the first case, the P2 and P3, the short bursts, arrived after the long bursts, so they had to wait all of that amount of time. Okay, so let's move on to the next one. So we're going to look at another algorithm. This one is called the shortest job first. So if we think about the last example, what made the improvements in wait time so much is the shortest jobs got to be executed first. So we didn't get that convoy effect. So this algorithm says, well, why don't we make that our algorithm? We will when the CPU is available, we'll look at all of the processes in the ready queue, and whichever one has the shortest burst, we will give it to the CPU, right? And so that's kind of the strategy there. Okay, so that's the shortest job first. There's two scenarios with that. There is a non-preemptive and a preemptive. So there's two versions of this. So the non-preemptive says that once a process gets the attention of the CPU, it gets to keep it until it finishes its burst. Okay. The second one, the preemptive, says that, well, if a new process happens to arrive into the ready queue while a process is on the CPU, the scheduler is going to make a decision. It's going to examine the processes in the ready queue and see which one is the shortest. And it will also include whichever one is currently on the CPU to see how much time it has remaining, right? And if the process that's on the CPU, if its remaining time isn't the shortest, then we're going to preempt it. We're going to pull it off of the CPU and put the shortest job. Okay. The shortest job first is is actually provably optimal in terms of waiting time. So it does give the minimum average waiting time for a given set of processes. So let's move to the next slide. So we're going to do a few calculations. So I will zoom in. Sounds like a lot of sorting. Yeah. Well, you could keep a heap data structure that keeps the shortest thing on top. The heap data structure is just a data structure that where you don't actually have to sort everything. You just need to and the heap data structure. I'm sorry, I'm using a word that's the same as that area of memory, but that's what the data structure is called. It's a nice way of representing something called a priority queue, and it has a log n um, time complexity, so it's real fast. So we don't have to do a major sort. If we keep it as a heap, um, uh, then we can always quickly get to. So we're keeping the queue as this heap data structure. We can quickly get the smallest or largest, whichever way we order the heap. Okay, so we're going to add a little bit more detail to the examples. So we're going to have the three processes again, but this time, rather than just saying, okay, all the processes essentially arrive at the same time, we're going to say they arrive at different times. So we've got three processes. P1, burst duration 24, it arrives at time 0. P2, burst duration of 9, arrives at time 2. Process 3 has a burst duration of 5 and arrives at time 4. All right, so that's kind of the idea. So in a first come, first serve scenario or algorithm, it's whoever arrives first, they get the attention of the CPU first. So P1, P2, and P3 will be put on the CPU in that order. So the Gantt chart for that would look like what you see in the lower left. P1 gets on for 24 time units. Meanwhile, at time 2, P2 arrived, so it will have been waiting on the ready queue from time 2 to 24. But at time 24, process 2 gets on, and then it finishes 9 time units later at time 33, at which time process 3 gets on. And remember, process 3 arrived at time 4, so it has been waiting quite a long time, from 4 time units to 33 time units. So let's calculate the average waiting time. So in the lower left, I'll just make that a little bit, make that a little bit bigger. So, so process 1 didn't wait at all, so that's 0. Process 2 waited from time 2 to time 24, so a total of 22 time units. Process 3 waited from time 4 to time 33, so a total of 29 time units. So you add those up, 22 plus, no, did I do that wrong? Oh, no, I didn't. Okay, I got lucky. 22 plus 29 is 51. So that gives us a total, an average time of 17.0. We can do the same math to calculate the average response time. So remember, the average response time is how long response time is how much time did it take for the CPU to get some attention, to take the process to get some attention from the CPU. So in this case, it's going to be identical to the waiting time, right? And so we get the same response time and the average turnaround time. So you calculate turnaround time is the arrival time, the finish time for the process minus the arrival time. So process 1 finished at time 24. It arrived at 0. So turnaround time for that was 24. Process 2 arrived at 2, finished at 33. So the turnaround time is 31. And process 3 finished at 38, arrived at time 4. So that's 34. So its turnaround time was 34 time units. You add all of those numbers up, but 24 plus 32, that gives us 56, plus 34, looks like, oh no, 24 plus 31 gives us 55, plus 34 gives us 89. You divide that by 3, the total turnaround time is 29.6. All right, so if we do the same thing for the non-preemptive version of the shortest job first, the total waiting time on the SGF side is wrong. Okay, I'll fix that, Richard. We'll just go over that. Okay, so yes, I see that. I see that now. Okay, so what is the total waiting? Let's go over the scenario here. So P1 does arrive first. It gets hold of the CPU. It's the only thing in the ready queue. So it gets to go on the CPU. At time 2, process 2 arrives. Now it is shorter. At time 2, process 1 still had 22 more time units to execute. Um, but this is a non-preemptive version of the shortest job first. So we don't kick P1 off of the CPU. Okay, so P1 gets to stay on. At time 4, P3 arrives. And again, we don't kick P1 off. So we get all the way down to time 24. Now that process leaves the CPU, and now the system has to make a decision. There's 2 processes in the ready queue, P3 and P2. Which one is shorter? Well, P3 is shorter. So P3 gets to go on rather than P2. So we put P3 on the CPU, and it runs, and it's non-preemptive, so it finishes, it does its 5 time units, and then P2 can get on. So now if we do our calculations, we get 0 for P1, then process 2, oh, I put process 2 over here. Sorry, I wanted to keep the order there. I should, so I'll just say P1. Yeah, I usually do my best to keep the ordering the same. I guess I got mixed up here. So P1 doesn't wait at all. P3 waits from time 4 to time 24. So it waits 20 time units. Remember, P3 gets on right there. And P2 gets on at 29, but got into the ready queue at time 2. So it waited a total of 27. So 20 plus 27 equals 49. So let's fix that. Sorry, equals 47. All right. And similarly, that number will be a little lower. So that'll equal 15. I should have used the text tool. 15.67. Right. So if you look over here, it is an improvement, isn't it? So we went to the shortest job first, non-preemptive. We improved the total wait time went to 47. Not a great improvement, but still an improvement. The average waiting time is down a little bit. There's no difference in the turnaround time, but the response time, remember, will be in non-preemptive cases the same as the waiting time. Can't see anything being. Oh, sometimes that happens, Richard. All I was doing was I was correcting the math on the right-hand side. Yeah, unfortunately, you kind of have to leave and join again. It's seems to be the that fixes that. Okay, so that is that. Okay, so we can see that certainly shortest job first. Um, Shortest job first uh, did improve it. For the shortest job first, average turnaround time. Oh, did I do the math wrong there too? Should it be? Let's have a look here. So that's P1 and P2. Yeah, that should have been, yep, yes. So that should be 38 minus 2. Yes, because I'm talking about P2 there. Yes, so my numbers will be off again. And that one, is that one right? P2, yes, that, no. Oh, no. This one, yeah, that one, 29 minus, yes, this one is right. That is P3. There we go. And so, yeah, is the math off? 24 plus 25 plus 36. Yeah, 24 plus 36, 60. Yeah, I guess that should be 80. Yeah, should be 80, 85 divided by 3 equals, what does that equal? 20, 28.3. That may be off a little bit there. Close enough. So we do see an improvement in turnaround time as well. So let's move. Just a quick question too: is Richard? Are you back? And can you? And did that fix the problem? Oh, that's great. Okay, so we'll just move to the next slide. And okay, so now what I'm going to do is, so I basically copied. Let me just. Yeah. I just copied that from the previous screen. Okay, so that we can compare the non-preemptive to the preemptive. Albeit we've got a couple of errors with the math there. Um, but yeah, notwithstanding that, we'll come back and we'll now compare it to the preemptive version. So the key thing to keep in mind with the preemptive version is every time the ready queue changes, the CPU has an opportunity to make a decision. All right. So in this case, we've got time 0. Nothing is in the ready queue, so P1 gets to go onto the CPU. At time 2, P2 arrives, right? And so the CPU can make a decision. Well, at time 2, P1, how much more processing does it need to do, right? So, at that time, it's 22 more. It's got 22 more time units to execute. So at that time, there's two things in the CPU. P2, or sorry, in the ready queue. You can think of it that way. P2 and P1, whose burst time is now 22, or its remaining burst time. So 9 is definitely shorter. So P2 gets the attention of the CPU. So P1 gets preempted. Okay, so we pull P1 off the CPU and P2 gets to go on. Then at time 4, right, P3 arrives. Okay, well, now the CPU can make another decision. So at time 4, P2 now has 7 time units left to uh, of its CPU burst to finish. And so the scheduler is going to say, okay, what's the smallest of these three times? Well, it's P3. Okay, well, I'm going to preempt P2 and I'm going to put P3 on the CPU. So now P3 gets the attention of the CPU. It stays on the CPU until it finishes at time 9. And then the scheduler looks into the ready queue and says, okay, what's left in the ready queue? Well, it's these two guys. Which one is the shorter of those two? Well, it's P2. Okay, P2 gets the attention of the CPU, gets to run its looks like I did the math here wrong as well, right? I'll clean this stuff up and post corrected math. So that should say times 16, shouldn't it? Yeah, it should say times 16. So that means all my math is going to be off. We'll just say it's 15 just for the math. And then once P2 finishes, it goes off the CPU and then P1 can get on. Right, so that's the preemptive algorithm. Okay, now when we do the average waiting time, we have to look at all the amount of time that a process spends on the ready queue. So in this case, P1, how long was it in the ready queue? Well, it was in the ready queue from time 2 to time 15. Let me just draw a line here. So P1 spent that amount of time. Okay, so P1 spent that amount of time in the ready queue. So that's 15 minus 2. I know it's actually 16, but just for the sake of the math here, 15 minus 2. And how much time did P2 spend in the ready queue? Well, when it arrived, it didn't spend any time in the ready queue because we preempted process 1, right? But then it did spend time in the ready queue from, let me just, from there to there, right? So from time 4 to time 9. Okay, so P3 spent no time in the ready queue at time 4. It was the shortest. It got the attention of the CPU and it got to finish. So P3 spent 0 amount of time. Right, so P3 spent 0 amount of time. P2 spent 9 minus 4 time units amount of time, which is 5. And P1 spent 15 minus 2, actually 16 minus 2, but again, for the sake of the math, add all of those up, we get to 18, divide it by 3, the average wait time is 6. Again, a pretty dramatic improvement. All right. Okay. And the average response time. This is an interesting one. So the average response time is actually 0, isn't it? Because P1 got a response as soon as it arrived, P2 got a response as soon as it arrived, and so did P3. So the response time is actually 0. The average turnaround time is also a fairly dramatic increase as well. And we do the calculations in the same way. All right, let's see, how am I doing for time? Sorry, why P1's burst is 22. So its burst would be 22 at this moment in time, at moment 2. So it starts off at 24, but it got the attention of the CPU right away, spent two time units on the CPU, which means at time two, it only had 22 more time units left in its burst. So that's why I crossed it out and put 22. So it was at time two, it only had 22 time units left. Similarly, that was what happened to P2 at time 4. Does that make sense? Okay, great. All right, let's see where we are next. Okay, so the shortest job first is it's an optimal algorithm, but there is kind of this problem, um, and that is, how long is the next CPU burst for each job in the ready queue, right? So how can we know that? Well, the answer is, uh, we don't know. Um, we don't know. Uh, because we would have to look to uh, we would need to we would need to look into the future. We would need to be able to predict the future, right? And we can't do that, right? So that is kind of an inherent problem with this algorithm is you need to know what a process's burst time is going to be, and a process's burst time, is most of the time I would expect is not known. Okay, so what do we do? Well, one of the things we can do, and it's a very good strategy for um, a lot of predictions. It's good in actually a lot of aspects of life. If you ever need to predict the behavior of something, just look at its past behavior. That is probably the best predictor of future behavior. So what we could do is we can estimate the length of CPU bursts based on the length of CPU bursts for that process in the past. If a process had um, short CPU bursts in the past, they're probably going to have a short CPU burst. Um, so what we do is we can use this little formula or strategy. It's called exponential averaging, and we just kind of keep track of the previous bursts. And so if we want to predict, if we want to, so if we think of T of n as being the actual length of the nth CPU burst for a process, and T of that's a tau actually, tau, the Greek letter tau, n plus 1 is the predicted value for the next CPU burst, so the n plus 1th CPU burst, then we can do this. We can say we can use this formula that the it should say n plus 1. Let me n plus 1. N plus 1. The next predicted CPU burst will be a proportion of the last um, the actual real CPU length, the burst length, and a proportion of the last predicted CPU burst length. And it ends up kind of making this kind of an exponential average of the previous CPU bursts. So, um, and we would give the most important weighting to the CPU burst um, that had just happened. All right, so that's called exponential averaging. It's worthwhile playing around with that a little bit just to get a feel for it. It's a common way to predict past behavior. I see my time um, has just expired. Are there any? Actually, it expired a couple of minutes ago. Sorry about that. Any questions before we call it quits. So I will be in the lab. So under a different link in a little less, in about a half an hour. Um, and so if you want to, so when I say I'm in the lab, I'm not physically in the lab. I'm meaning I'm opening up one of these collaborate sessions um, for the lab, and everyone is welcome to that. And we're working on Lab 8. Okay, and then I'll have, I think the next lab, I think it is on scheduling algorithms. Um, so yeah, we'll see how that goes. All right. Any questions? When do you schedule the sort quiz or the short quiz? Um, I don't know. Like the little sample quiz. If I do post the sample quiz, uh, it really is dependent on my time. Uh, I'm I'm I am kind of struggling with cobbling together slides and things like that. And I'm not sure yet how to use the quiz tool properly. So I'm learning about that right now. Um, so I'll do my best to give you as much advance as possible for that. Um, but it certainly won't be for the next few days anyway. Okay. Yeah, you do have the sample midterm that's up there, so the questions will be similar, right? And we also have another lecture between now and then. So, um, yeah, if there's anything else I can, yeah, do to help things along, I'll do my best to get on top of that sample quiz because we want to make sure too that everybody, it's working well for everybody from home or whatever devices you're using. Any other questions? Okay, stay safe, everybody. And as I mentioned again, I'll be in the lab version of Collaborate in about a half an hour. All right, so take care. Thanks, everyone.